When a patient record system goes down for 2 hours during an availability zone failure, the costs mount fast: regulatory exposure, lost revenue, and a scramble to explain what the architecture was supposed to prevent. The difference between 2 hours of downtime and automatic failover in under a minute often comes down to one architectural choice. Stack lessons here. Let's get you exam ready. By the end of this checkpoint, you'll understand when each resilience pattern actually works: multi-AZ versus read replicas, each load balancer's real constraints, and which disaster recovery strategy fits your cost and recovery time targets. These patterns matter in production, and they show up on the exam because of it. Over the last several episodes, you built up the whole resilience toolkit. You covered multi-AZ versus read replicas, the load balancer types, the 4 disaster recovery strategies, and the Route 53 routing policies. And you worked through SQS, SNS, and Kinesis for decoupling. Now we'll apply those patterns to real production decisions. How to pick the right one when cost, compliance, and recovery time all matter. The fastest way to pick the right architecture is to first understand what each service can and cannot do. Once you know those hard boundaries, capability violations rule themselves out. An option that asks a service to do something it fundamentally cannot do, eliminate itself. You don't need to compare it against anything. That leaves you with the options that actually work for the scenario. Scenario 1. A patient records database has to survive an availability zone failure. The requirement is spelled out precisely. Failover must happen automatically, and there can be 0 data loss. On the table, you've got multi-AZ, a read replica, and an option that says to read from the standby. Notice those last two both sound like they involve a second copy of the data. Which of these 3 actually meets the failover requirement? Think about what happens when an availability zone fails, which one automatically switches traffic with 0 data loss, and which ones would leave you either losing rights or waiting for a manual intervention. Start with the capability violation. Reading from the standby is impossible. The multi-AZ standby serves no traffic at all until failover promotes it, so that option is dead on arrival. Then the read replica. It replicates asynchronously and promotion is manual, which means recent writes can be lost and nothing happens automatically. Both fail. That leaves multi-AZ and it fits perfectly. One note on terminology: there are actually 2 multi-AZ deployment models. The classic multi-AZ DB instance gives you one synchronous standby in another zone, automatic DNS failover in 60 to 120 seconds, and 0 data loss by design. And that's the model this scenario is describing. The newer multi-AZ DB cluster gives you 2 standbys and uses semi-synchronous replication instead. For scenario questions about automatic failover with no data loss and a single standby, the classic DB instance model is the answer. And Amazon Web Services says it in plain words. The high availability option isn't a scaling solution for read-only scenarios. You can't use a standby replica to serve read traffic. That single sentence kills the read from standby distractor every time it appears. Classic single standby multi-AZ is for availability, full stop. Scenario 2. A trading platform ingests raw TCP market data feeds. That's not HTTP. It's a straight layer 4 protocol. And the exchange's firewall requires a single fixed IP address to add to its allow list. Your options are the application load balancer, the network load balancer, and the legacy classic load balancer. The exchange needs a fixed firewall rule, and it sends raw TCP, not HTTP. Which load balancer can actually accept an elastic IP and operate at layer 4? Pause here if you want more time before I walk through it. The application load balancer is layer 7 only. It lives behind a DNS name with dynamic IP addresses, and you cannot pin an elastic IP to it, so it fails the static IP requirement outright. The classic load balancer is the sneaky one. It does handle TCP, which tempts people, but it also cannot be assigned an elastic IP, and it's legacy. So it's a pure distractor. That leaves the network load balancer, layer 4 for raw TCP, a static IP per zone with elastic IP assignable at millions of requests per second. The documentation is explicit. Each network load balancer node in the zone gets a static IP address, and for an internet-facing load balancer, you can optionally associate one elastic IP per subnet. That's the deciding capability. The moment a scenario says static IP, elastic IP, or firewall allow listing, the answer is NLB. Scenario 3. A batch analytics backend needs a recovery time objective measured in tens of minutes, and cost has to stay low. The team can't justify paying for duplicate compute sitting idle. 4 options this time: backup and restore, pilot light, warm standby, and multi-site active-active. The business needs to recover in tens of minutes without doubling infrastructure costs. Which strategy meets both constraints? Think about where each option sits on the cost and recovery time spectrum before I reveal it. Work the edges first. Backup and restore covers in hours, so it misses the tens of minutes target. Active-active gets you near 0 recovery time, but at roughly double the cost, it's disqualified by the low-cost constraint. Warm standby is the tricky one. It recovers in minutes, faster than we need, but it keeps a scaled-down copy running the whole time, so it costs more than the scenario allows. That leaves pilot light. The data core replicates continuously, compute stays switched off, and you turn on servers and scale up at failover. Tens of minutes, minimal ongoing cost. Here's the exact line that separates the two. Pilot light cannot process requests without additional action taken first, whereas warm standby can handle traffic at reduced capacity immediately. So the anchor question is simple. Is compute already running? If yes, warm standby. If it's off and you have to turn it on, pilot light, which is why pilot light is cheaper and slower. Scenario 4. A GDPR data residency rule says EU users must be served only by EU endpoints. That word must is doing a lot of work. This is a legal boundary, not a performance preference. The options are geolocation routing, latency-based routing, and geoproximity routing. GDPR says EU users must stay in EU regions. Which routing policy enforces that on every request, not just most of the time? Lock in your answer before I give it away. Latency-based routing sends each user to the lowest latency region, which means on a fast day, a Paris user could land in Virginia. That breaks residencies, so it's out. Geoproximity routes by location with a bias style, but it's about shifting traffic between endpoints, not enforcing a strict legal boundary. So it's the nuanced wrong answer. Geolocation is the fit. It routes by the query's continent, country, or even US state, and it enforces that deterministically on every query. It's the one policy purpose-built for residency and content restriction rules. Last one, an order of PI spikes to hundreds of requests per second during a flash sale. Downstream, a single consumer group can't keep pace, and it absolutely must not drop any work. The options are SQS, SNS, and Kinesis data streams. During the flash sale, thousands of messages pile up while one consumer drains them. If the consumer goes down, can you afford to lose those orders? Which service buffers without dropping work and holds the backlog until the consumer is ready to continue? SNS pushes every message the instant it arrives with no persistence. If the consumer is slow or briefly down, those messages are gone. That violates the no loss work requirement, so it's out. Kinesis could technically buffer, but it's built for ordered replayable streams across multiple independent consumer groups, and it drags in shard management. For one slow consumer, that's overkill on cost and complexity. SQS is the clean fit, a pull-based queue that absorbs the burst, lets the consumer pull at its own pace with up to 14 days of retention, and never blocks the producer. Here's the whole set on one board. Automatic failover with no data loss, maps to multi-AZ. Static IP on a non-HTTP service, maps to NLB. Tens of minutes recovery at low cost maps to pilot light. Residency that must stay in region maps to geolocation. And a spiky producer with a slow consumer maps to SQS. Notice the left column is all qualifiers. Train your eye to that column, and the answer on the right falls out on its own. So carry these 5 forward. Automatic failover with no data loss means multi-AZ, never read from standby. A static IP on a load balancer means NLB, never ALB or CLB. Tens of minutes recovery at low cost means pilot light, not warm standby or active-active. Residency compliance means geolocation, not latency or geoproximity. And a spiky producer with one slow consumer means SQS, not SNS or kinesis. And every one, you got there by eliminating the capability-violating option first. Now let's lock it in with a quick 5-question quiz. Question 1. A hospital's patient records database must fail over automatically on an availability zone outage with no data loss. Which RDS configuration meets both requirements? Option A, a cross-region read replica that's promoted on failure. B, classic single standby multi-AZ with synchronous replication. C, a read replica in the same zone serving both reads and failover. Or D, multi-AZ with a standby serving reads to reduce primary load. Lock in your answer before I give it away. This one is B. Classic multi-AZ gives you a synchronous standby and automatic D and S failover. That's zero data loss with no manual step. The read replica options replicate asynchronously and need manual promotion. And option D is impossible because the multi-AZ standby never serves read traffic. Question 2. A partner's firewall must allow list a single fixed IP address for a raw TCP market data feed. Which Amazon Web Services load balancer satisfies this? A, an application load balancer with a static DNS name. B, a classic load balancer since it supports TCP at layer 4. C, a network load balancer with an elastic IP per availability zone. Or D, an application load balancer fronted by a WAF Web ACL. Pause here if you want more time. The right call here is C. Only the network load balancer runs at layer 4 for raw TCP and can hold a static elastic IP per zone. The application load balancer sits behind dynamic IPs, and the classic load balancer handles TCP but can't be assigned an elastic IP, which is exactly why it's a distractor. Question 3. A batch analytics backend needs a recovery time objective in the tens of minutes, while keeping ongoing disaster recovery costs as low as possible. Which strategy fits? A, pilot light, with data replicating continuously and compute switched off. B, warm standby, a scaled-down copy running continuously. C, multi-site active-active across 2 regions. Or D, backup and restore from cross-region snapshots. Think about which constraint matters most here. The right call here is A, pilot light. The data core replicates continuously while application compute stays off, which lands you in the tens of minutes at minimal cost. Warm standby is faster but more expensive. Active roughly doubles cost. And backup and restore recovers in hours. Too slow. Question 4. GDPR requires that EU users are always served only by EU-based endpoints, regardless of network performance. Which Route 53 policy enforces this? A, latency-based routing to the lowest latency region. B, geo-proximity routing with a positive bias toward EU resources. C, weighted routing split across EU and non-EU records. Or D, geolocation routing scoped to the Europe continent. Run the decision rule from earlier before you answer. If you said D, well done. Geolocation routing enforces a deterministic geographic boundary, continent, country, or US state, on every single query. Latency and geoproximity optimize for speed or proximity, so either one could send a Paris user outside the EU on the wrong day. Last question. An order PI spikes to hundreds of requests per second, but a single downstream consumer processes slowly and must never lose a message. Which service is the right buffer? A, Amazon SNS, publishing each order to a topic. B, Amazon SQS, with the consumer polling at its own pace. C, Kinesis data streams, with a single shard consumer. Or D, SNS fan out to multiple email subscribers. Got your pick? Let's see. It has to be B, and here's why. SQS persists every message until the consumer processes it, so bursts get absorbed and nothing is dropped. SNS pushes with no persistence, meaning a slow consumer loses work and Kinesis piles on shard management and replay that a single consumer just doesn't need. That's checkpoint 2, Resilient Architecture's Retrieval Challenge, start to finish. Subscribe to the rest of the Cloud Architect path. It keeps these in front of you and helps them reach new students. Tell me in the comments what made it click. If there's a certification you want me to tackle next, request it below. And if the speed or style could be better for you, say so. I tune to feedback. Until next time.